Welcome to the AP Physics video lecture. This is on Unit 4 Energy. The topic is on kinetic energy. What is kinetic energy? Kinetic energy is defined as energy of a moving mass with a speed over time. The formula for that is going to be K is equal to 1/2 mv squared. K is the letter we use to associate with kinetic energy. M is the mass. V stands for the velocity. Anytime this object moves, there is a velocity associated with it. Once an object moves, we can associate that with kinetic energy. Note, anytime an object moves, it has kinetic energy. Here are some questions. 1. What happens to the kinetic energy if the mass of the system decreases by half? We would say that the kinetic energy will also decrease by half. This goes down. So this goes down. So an object with smaller mass will have less kinetic energy moving at the same velocity. Question 2. How much will the kinetic energy change if the velocity is now doubled? So this becomes 2x. What happens? 2x squared becomes 4x. So we would say that the kinetic energy will increase by a factor of 4. Question 3. How much will the kinetic energy change if the velocity is now cut in half? So velocity is now going to be 1/2 x or 1/2 v. 1/2 squared is 1/4. You can say that the kinetic energy will now decrease by a factor of 1/4. This should give you the relationships. The kinetic energy is directly linearly proportional to the mass. So the mass in question 1 went down by 1/2, so kinetic energy went down by 1/2. That 1-to-1 relationship is our direct linear proportionality. Then we would say that the kinetic energy is directly squared proportion to the velocity. The squared part comes from that number being squared to the exponent of 2. When it doubled, it went to a 4. When it was halved, it went to 1/4. That number squared. That's why you would say that the kinetic energy here is directly squared proportional to the velocity of the object. When we look at kinetic energy, it's always good to look at the change of the kinetic energy. The change in kinetic energy can be understood as describing how much work is being done. This is also related to something called the work energy principle. This person that is moving this block, and we know that this block has a kinetic energy because the block is moving. It started from rest, then over time, you would see that the block moved 5 meters. This is the same thing as when we talked about work, because work is defined by force times distance. So this is how work energy are connected. That's why they call it the work energy principle. The change in the kinetic energy is the same thing as the work being done. In simple English, you can see the formula as the net work done on a particle is equal to the change in the kinetic energy of the particle. Breaking down the kinetic energy part, you can just say it equals the kinetic energy final, which is after, that's your final, minus the before, which is the initial. The net work done can be seen that. If we arrange things using algebra by just adding the kinetic energy to both sides, you can say that the kinetic energy after, so this is the final kinetic energy, is equal to the initial plus the work done, which is the person moving the block. This is a very good conceptual understanding of what kinetic energy is. Let's do some problems to give you a better understanding. A person is pushing this block on a frictionless surface with a constant force of 12 newtons. The block travels a total of 5.0 meters in the span of 3 seconds. Determine the mass of the block. Let's label our information. The force applied is 12 newtons. The distance is 5 meters. The time is 3 seconds. To do this, our answer is going to require us to use the work energy principle. Here's the equation. W net is equal to 1/2 mv squared minus 1/2 mv naught squared. Notice this is going to require me to have the velocities. My initial velocity was 0 because the object was at rest. Notice in this scenario, the object started at 0 velocity. It was at rest. Okay, take a look. Then in the end, the final velocity, notice it traveled 5 meters in 3 seconds. So you can say that the velocity is 5 meters per 3 seconds. You can plug that in. I made the substitution that work net is equal to force times distance. Plug in the values. Notice that this is going to be equal to 0 because the object started at rest. Plug in the values in here. Now you can rearrange to get this answer. If you want to see the complete algebra, it should look something like this. 1/2 m. This becomes squared, so this becomes 25 over 9. Then you're going to multiply by 1/2, then multiply by 9 over 25 to get m. That's how you get rid of the constant on the right hand side. That's how you get 43.2. All right? That is the mass of the block. Same question, same scenario, but the question asks, determine if the system is actually open or closed. Well, we know from our last problem, the work done was 60 joules. We should have seen it right here. That was the work done right here. That's the 60 joules. And we also saw that the kinetic energy was equal to 60. So if you plug it in here, 1/2 mv squared, and the m here is 43.2. You plug it in here, you should get kinetic energy equals to 60 joules. There are two different answers here. They're answering the same thing, but there's two ways of answering it. Notice that the initial kinetic energy was 0 because the object was at rest. The first answer, you would say there is a positive 60 joules of work in there. Therefore, the system has to be open. The energy had to be coming from the energy has to be coming in from somewhere into the system for it to do work. So this person is only moving this block because energy is coming in. Okay? This energy is coming into the system. The energy that is coming into the system is the person pushing it. So there's an energy being expelled by that person. Or you can say that there's a change in 60 joules of energy. At the start, there was 0 joules of energy because it was at rest, but at the end, there was 60 joules of energy. That increase in that 60 joules of energy had to come from somewhere, therefore the system had to be open. Let's take a look at the graphical way of looking at the change of kinetic energy. Here it says a student conducts an experiment in which different objects are released from the rest above a motion detector so that the data can be collected about the object's motion as the object falls to the ground. All the objects here have the same mass. The experiment is conducted near the Earth's surface. All frictional forces are considered to be negligible unless otherwise stated. First question, which object has the greatest speed at 2 seconds after its drop? Well, we know that this is kinetic energy. Kinetic energy is defined as 1/2 mv squared. You're comparing them, so I don't care about the 1/2. They all have the 1/2, and they all have the same mass. Right here, notice it says all the same mass. So I'm just gonna delete it. Okay, so the kinetic energy can be seen by just looking at the velocity. If we look at the 2 seconds that it's asking for, we see here, here, and here. We should see that the green is actually higher. So here it would have a higher kinetic energy. Therefore, it's going to have a higher speed at that time. Next, what object has the greatest speed at the end of the drop of 5 seconds? Well, all the objects here has the same kinetic energy at the end, which is right here at 5 seconds. They all have the same of 250 joules of energy. You can solve for the velocity if you would like. But notice that they all have the same kinetic energy, so they're going to have all the same speed. Lastly, which object experienced the most work done by the force of gravity, causing it to fall down? Well, we would say that all the objects here have the same amount of work, because the way we define work is a change in kinetic energy. So this is the kinetic energy at the start, kinetic energy final. Notice that everyone here has the same path. Their starting and their ending are the same. And their ending is 2,500 joules. Therefore, you can say that their work is all the same. So when we take a look at change of kinetic energy, we are only looking at the starting kinetic energy and the final kinetic energy. No one cares about the in-between step. All right. So there you go. That is everything that you have to know when it comes to kinetic energy.